All right, the next problem I think is this one, the density of nitrogen. So we can calculate the density using the equation. Actually, they give us the density, 1.07 grams per liter under these conditions here. Explain how this shows that the formula of nitrogen is N2 rather than just N. Well, if we know the density and we know these, the atmospheres and the temperature, then we can calculate this molar mass. And the molar mass is related to the density. And so let's see here. So the molar mass is equal to mRT over PV. M, mass over volume, is the density. So we have the density times RT divided by P. So the density times RT divided by P here. And we get 28 grams per mole. If it's N2, it's 28. If it's just M, it's 14 grams per mole. So since it's 28, it's got to be 2 nitrogens there. So it's going to be N2. At a given temperature and pressure, what mathematical relationship exists between density and molar mass of gas? Well, this is the mathematical relationship right here. You can derive that from the ideal gas law. It's probably it here. They're deriving the equation in terms of density. Density is mass over volume, and then we substitute volume is equal to nRT over P. So nRT over P, invert and multiply. And then mass over moles, M over N is molar mass. So they skip this step here. You got the molar mass. So they're calling P over RT K. This is kind of constant. You don't have to do that. The K changes the temperature and pressure. So I'd ignore this K business here. 56. Labels have become detached from cylinders of two gases, one of which is known to be propane, the other butane. The densities of the two gases are compared at the same temperature and pressure. The density of gas A is 1.37 grams per liter. The density of gas B is higher. So which one should have a higher density? In other words, which molecules weigh more, propane or butane? Butane weighs more, therefore it's going to have a higher density. You're going to have the same number of molecules per volume. It's just that the molecules weigh more for butane than for propane. Both butane and propane are used for cooking. And so they say butane, C4H10, has a higher molar mass, 58, versus propane, which is 44. Actually, they calculate the difference in density you'd expect by looking at the proportion of masses here. They didn't ask to calculate it, they just asked which one is which. 57, organic chemist has produced a solid that she believes is pure. She expects a molar mass of 346. Using 4.08 grams of solid, she melts and then boils it into a 3.36 liter vacuum chamber at this pressure and this temperature. She was disappointed the molar mass is close to what she expected, but not close enough. What molar mass did she find? So we could just plug in the numbers in the molar mass equation here. You know, in this case, we're given the mass and the volume. We're given the mass and the volume, we know the density. So here's the mass. The volume is 3.36 liters. So essentially that's density there. Times RT over P. And that calculates to 334 grams per mole. 334 grams per mole versus 346. That's what she was supposed to get. This is what she got. And so they're quite a bit off. It could be any number of reasons that it's off. Her findings suggested to her what her mistake might have been. Does it suggest anything to you? Not really. Yet. Let's see what they say. The difference between the expected molar mass and the molar mass that was found experimentally was 12 grams per mole. This is atomic mass of carbon. Perhaps she has one too many carbon atoms in her expected molecule. This answer, to me, is nonsensical. It's a ridiculous answer. I think part B is, I mean, how do you miss a carbon atom and a molecule? You know, that's the difference between propane and butane. The difference between propane and butane is the CH2. But I don't really see how you miss it. Unless it's okay, maybe. All right, so that's the end of chapter 14. We're going to look at chapter 15 now. Chapter 15 deals with gases, liquids, and solids. And so what I decided to do with this chapter is I'm going to go out of order presentation with you in the book. I'm going to go out of order just so I can save some time. So what I'm going to do is I'm going to go to solids. First, and then to liquids. For example, if you heat a solid, this would be the symbol for heat. If we heat a solid, what's going to happen? Well, the solid's going to warm up until it hits a certain temperature at which it melts. That temperature is called the melting point. So eventually, as we heat this up, it's going to melt into a liquid. And so what's the difference between a solid and a liquid? Solid will go into a liquid. What's one of the major differences between a solid and a liquid? One has a fixed shape, a solid tube. The other conforms to the shape of the container.
Has vibrational motion, the other one has another kind of motion.
Actually, both have vibrational motion. Vibrational motion is allowed.
Yeah, but the liquid has another one.
Yeah, right. Liquids have, well, both solids and liquids might have rotational, although solids, it depends on what type of solid it is. But you're right, rotational. But the key one is translational. So liquids have translational motion. So what has to happen here is the solid is held together. What holds solids together? What holds solids together are bonds. What types of bonds do we have? We have ionic bonds. We have covalent bonds. And we have metallic bonds. Some solids aren't held together by chemical bonds, like ionic, covalent, or metallic, like ice. When we think about ice, what holds the water molecules together? There are bonds that hold the hydrogens to the oxygens, but what holds one water molecule to another water molecule in ice? It's not a chemical bond. What holds those together are what we call intermolecular forces, or IMFs. Intermolecular forces. And so, when I look at the particles of water in ice, they aren't bonded together. They're held together by IMFs, intermolecular forces. There are three major intermolecular forces that we look at in order of increasing strength. One is called the instantaneous dipole. There are other names for this. Instantaneous dipole also goes by the name of, let me write that down here, also known as induced dipole. Or Another name for it would be instantaneous hyphen induced dipole. Another name of this would be London force. Another name for this would be dispersion force. All these refer to the same thing. We have the instantaneous dipole. We have the dipole force. And we have the hydrogen bonding force, or H bond, plus some others, which we'll talk about. Others, such as the, what's called the ion hyphen dipole, the ion, etc. So what happens is, in a solid, we have to partially break the bonds that hold the particles together so that the particles can translate. But we can't completely break it. If we completely break the forces that hold the particles together, then do you know what we get?
Yeah.
A gas, right? And so if we were to heat this up more, that is, if we continue heating up a liquid, we're going to get a gas in which there are no forces holding the particles together. The particles are completely broken apart. And so what we say for this, for solids, for example, for solids, we say that the bonds or the IMFs, bonds/IMFs, are stronger than the temperature. Temperature is a measure of what? Temperature is a measure of Ke. Ke stands for kinetic energy. So the bonds and intermolecular forces are too strong to be broken up by the motion. However, if we heat it, we're increasing the kinetic energy. So for liquids, the bonds and the IMFs are about the same as the kinetic energy. Kinetic energy. And so it's partially broken up, the bonds and IMFs that hold it. But for gases, basically the kinetic energy is too much. And so the bonds and IMFs are weaker than the kinetic energy. And, break everything apart. So I'm going to go a little bit backwards here. I'm going to start off with solids. Your book starts off with gases. Then moves to liquids and then goes to solids. But I'm going to start off with solids first. There are two types of solids. There's solids where everything's nicely ordered, and there's solids where it's slightly disordered. Do you know what those two types of solids are called? Yeah, crystalline and amorphous. And so we'll take a look at some examples here. Crystalline solids are pretty obvious. Sometimes it's not so obvious when you look at it, though, like this chunk of silicon. So here, when I look at this chunk of silicon, it doesn't look so crystalline, but it is. But when we look at the atoms are nicely packed, nicely arranged. Same thing with this crystal of aluminum. This chunk of aluminum is nice crystals there. This quartz crystal is easy to see from the outside. Things are nicely ordered. Oh no, this is not quartz. This is salt. These salt crystals are nicely ordered. You can see they look like cubes here. So these are all examples of crystalline solids. This plastic bottle is either semi-crystalline or amorphous. In some ways it's ordered. If you look at these carbons here, they look nicely ordered. But what's lacking is something called long-range order. As we go further out, it becomes less predictable where the atoms should be. Whereas in a crystal, it's pretty predictable where the atoms or ions should be in this case. So this is amorphous, that's crystalline. Now, so we have amorphous and crystalline solids. And what we're going to look at is we're going to look at the types of solids based on the forces that hold the particles together. But Let's take a look at these here. One thing about crystalline solids is, since they are well ordered, you know, they tend to fracture in more of a reproducible pattern or in some kind of pattern. So when we see crystals like diamond crystals, salt crystals like that, they can be cleaved. This is called cleavage here. Whereas amorphous solids, they don't fracture in any kind of pattern. This is called a conchoidal fracture here. And it's hard to predict how it's going to fracture compared to crystal. The breaking bonds there fracture. Now, we're going to look at types of solids. It doesn't matter if it's crystalline or amorphous. So this should say types of solids. The types of solids, whether they're crystalline or amorphous, are going to be determined by the bond or the IMF that holds the particles together. And so let's take a look at these. I'm going to go slightly out of order here. So we have ionic solids. Ionic solids can be amorphous or they could be crystalline. But what common feature all ionic solids have is they're held together by ionic bonds. And so ionic bonds are just the attraction between positive ions and negative ions. So we're going to build up a lattice like this. We're going to get a nice crystal. Ionic bonds are strong. So in order to partially break these apart, you know, we need pretty high temperatures. And so what we can say, a characteristic of ionic solids is they have a high melting point. Melting point is the temperature at which it melts, that is, translational motion. The ions are freed for translational motion. They aren't completely freed, that is, they can't escape into the gaseous state necessarily. They're free to translate into liquid. So once we melt that, then we're going to get molten salt. And so molten salt, now we got translational motion can appear. So these ions can move about in different directions. It's a liquid. It's a solid. Okay, but what are some of the other characteristics of the solid phase? So this would be molten salt here. Some of the other characteristics, in addition to the high melting point, is this. They have a high melting point. These are brittle. They're brittle because what happens is if you push down on this column here, if we push down hard enough, we're going to displace the ions. And so if we push down on this column such that the negative ion here is aligned with the negative ion there, and the positive ion here is aligned with the positive ion here. And so if we push this column down, then the negative sees the negative, the positive sees the positive, they're going to repel each other. And so this whole layer is going to break off. That's cleavage there. So that's what causes these to be brittle, but they have high melting points. They have strong bonds, as long as they're the right orientation. These are typically soluble in water. Water is what we call polar. And so water has a positive end and a negative end. So what happens is the water is attracted to these ions and starts to pluck these ions off the crystal surface, eventually dissolving the crystal. And water will be successful as long as the ionic bonds aren't too strong. If the ionic bonds are too strong, like in phosphates, carbonates,
ion bonds get too strong, then water is going to have a hard time dissolving things. These are typically non-conductors of electricity. You know, there's no translational motion, so they don't conduct electricity. However, molten salts are good electrical conductors, or aqueous solutions of ionic solids are good conductors of electricity because now we have translational motion and these ions can carry charge. That is, they can conduct charge, which is conducting electricity. And so basically what we're doing is we're partially breaking it up. Now when we break this up, are there ionic bonds here? What holds the ions together? What holds the ions together here are IMFs. IMFs stand for intermolecular forces, but molecular is used loosely because these are going to be interionic forces. And so what holds these together are ion-ion attractions. These ion-ion attractions aren't so strong that we call it an ionic bond. An ionic bond is a very strong ion-ion attraction here. These are going to be weaker than that because of the kinetic energy. The kinetic energy is disrupting things and preventing ionic bonding from occurring. And so basically it's just the positive and the negative charge that's going to keep this together from vaporizing out into the gaseous state. But eventually if we add enough kinetic energy, that is if we add enough heat, then the ion-ion attractions can be overcome. And the ion-ion attractions can be overcome and we're going to get a vapor that is a gaseous salt here. Okay, our solids, are they compressible? Can we squeeze them? Are solids compressible? No. Are liquids compressible? More than solid, but not really. They're not, I mean, all these are compressible to a small degree. But when we compare them to gases, are gases compressible? Yeah. Gases are easily compressible. And so, relatively speaking, we say solids are incompressible and liquids are incompressible, non-compressible. All right, so this is ionic solids, and so the classic example of an ionic solid would be like sodium chloride. Should be down here at the bottom right. Sodium chloride. Sodium chloride is going to have a high melting point. It's not really going to conduct electricity very well. Not unless it's molten or dissolved in water. Let's go on to the next type of solid. The next type of solid is called the covalent solid, or network covalent solid, or network solid. I'll just call it covalent. Covalent solids are held together by covalent bonds. So this is AKA network or network covalent. An example of a network covalent solid would be like diamond or quartz. Now, if we look at diamond, diamond is a whole bunch of tetrahedral carbon atoms. This, so these would be carbon atoms here. Extending it off in 3 dimensions. So is it easy to break covalent bonds or difficult to break covalent bonds? Difficult. And so if it's difficult to break the bonds, does it have a high melting point or a low melting point? High melting point. These have a very high melting point. Diamond and quartz, very difficult to melt. You got a high melting point. So if we do melt diamond, let's say we melt diamond, what are we going to get? We're going to get molten carbon. atoms. And these molten carbon atoms, they're going to form a liquid, so we're going to get liquid carbon, where the carbon atoms can now translate. But what holds the carbon atoms from vaporizing into the gaseous state? Something's keeping the carbon atoms together. Otherwise, the carbon atoms would like to be free and vaporized. Yeah, so what's holding them together are not covalent bonds. Do we have covalent bonds anymore? No, we've broken the covalent bonds. So now what we have are IMFs. Now IMFs, what they are they're weaker electrical attractions. Like ionic bonds. Ionic bonds are stronger electrical attractions between positive and negative. IMFs are weaker electrical attractions. And they're going to be between positive and negative. So we got the covalent bonds. Covalent bonds are also electrical attractions as well. Covalent bonds are electrical attractions because what happens is there's an electron cloud between. So these two electrons form an electron cloud like this. And the positive nuclei in the atom are attracted to this electron cloud here. The atoms are going to be held together. But what holds two carbon atoms together here? And so if we heat this, well, it hasn't vaporized in the gaseous state. The reason it hasn't vaporized is this. If I look at a carbon atom, is there a positive end and a negative end? In other words, is there a dipole? Dipole is two poles, a positive pole and a negative pole. Do you see a dipole on a carbon atom? There's no dipole. In fact, carbon has how many electrons? It has 6 electrons. And those 6 electrons are evenly dispersed in the shells here. So we got this electron cloud. The first shell's filled, the second shell's partially filled, but the electrons are kind of spread out, evenly dispersed. This electron cloud. That's like, if you go to a swimming pool, if you go to a swimming pool and there's nobody inside the swimming pool, then the water is evenly dispersed in the swimming pool. And so the water of a swimming pool is evenly dispersed. There are no waves or anything like that. But what can happen is this, although in the swimming pool it would be hard. What can happen is, can we pinpoint where the electrons are? No, we can't. That's because of, what was that principle? Some kind of principle that talks about pinpointing electrons. Pauli exclusion principle is different. Pauli exclusion principle says that no 2 electrons in an atom can have the same set of 4 quantum numbers. And so if that's the case, then that means we can only have 2 electrons per orbital. And so the Pauli exclusion principle tells us